So I'm going to talk about a couple of new modes and capabilities on NIRCam. But first, I just want to give an overview of the instrument a little bit and what the different modes are to help introduce you to what I'll be talking about today. First, just to remind you that we have two modules, Module A and B, and both of these modules have two channels. They have a long wavelength channel, which are outlined in red here, and then the short wavelength channel is in blue. In the long wavelength channel, there are just the two detectors filling the whole field of view, and in the short wavelength channel, there's the four detectors filling the field of view in each module. And then the field of view is about 2.2 arc minutes on each side for each module. We have 5 observing modes. The one that you're probably the most familiar with is imaging, and this is the main near-infrared imager for JWST. We've got 29 filters across both channels with multiple widths, and of course you get these beautiful images that you've seen before. We also have choreography, and choreography has 5 different masks used with LEO stops, and that allows you to call it the central star and do some direct images of exoplanets or disks or whatever you are looking at. I'm going to be talking a lot about time series today. We have 2 time series modes. There's the imaging time series mode, which just does transits as the exoplanet goes in front of the sun or in front of the star in just imaging. And then we also have the GRISM mode, which also does exoplanet transits, and but except now you get the spectroscopic information, which I've highlighted in yellow here in this example in WASP 107b. Which complements really well, MIRI's coverage and also Hubble and of course NIRISS and NIRSpec. And then we also have a wide field slitless spectroscopy, which uses the GRISMs in the long wavelength channel to disperse spectra in columns and rows so that you can disentangle the sources. But today I'm going to be focusing on just 3 of these modes. We have 3 new capabilities that apply to imaging and then to both the time series modes. So the first one is SuperStripe, which is a subset of this multi-stripe mode that you've heard about from the other instruments today. And that is a new mode that's going to be available in cycle 6. And then the next one is for moving target observations, and that applies to imaging. And this is allows you to subtract background stars and galaxies from your moving target observations. And then the last one I'm going to talk about is the short wavelength GRISM time series. And this is that DHS mode that you heard briefly mentioned by some of the previous presentations. And this is in addition to the previously existing long wavelength GRISM time series that we had. So I'm going to start with SuperStripe. And first, just a reminder of why the motivation for doing SuperStripe is that we have this multi-cum readout mode on the detectors that samples the detectors regularly as you go, as the flux accumulates up the ramp. But the bright limits are determined by the how long it takes to sample all of the pixels. So if you're in the full frame, it takes a full 10.7 seconds. The largest subarray that we have is about 4 seconds. And then the smallest subarray is 0.05 seconds. So you do have a pretty large range in brightness limits here, but it's still limited to pretty faint sources. And the problem is that the subarrays are quite small. Some of them are up in the corner up here. Hopefully you can see my cursor. Some of them are in the middle of the detector. And the problem with the middle of the detector is that there are these gaps in the short wavelength detectors here. And so if you want to image something that's bright and large, like Jupiter in this example, you have to do a lot of mosaicing and dithering and moving of the telescope, which is very inefficient. And so what we'd like to be able to do is not move the telescope and observe something bright like Jupiter in just one detector. And so that is the motivation for this SuperStripe mode. And what SuperStripe is it's very similar to what you've heard about already, but it works a little bit differently. And what it does is it takes a full frame image and then scans one stripe at a time up the detector. And that's what this is illustrating here. And you get reference pixels read out for each one of these stripes. So the reference pixels are down here on the bottom of the detector. And for every single one of those stripes that's red, you end up with a row of reference pixels at the bottom that's red from down here. And then when you stitch it all together, you get something like this, where you'll see all of the data plus the reference pixels interwoven between there. This is the level 1 data product. So it kind of looks a little stretched out because you have these extra reference pixels stitched in there. But then, of course, in the level 2 and the level 3, those reference pixels are used to correct the data, and they get extracted out, and you end up with just a clean image. And this is available for the full frame images and also for the very smallest subarray, sub 64p. So it's a 64 by 64 subarray. And that will, oh, and I do have a note down here that the smallest subarray doesn't always have reference pixels, but in that case, you are photon limited, so it's not as important to have them. And the result here is that the brightness limits increase dramatically. So I have here the old brightness limits in cyan for the smallest subarray and in purple for the full frame. And you can see these arrows showing where the 212 filter then is going to reside if you use the smallest super stripes. So for full imaging, now you can image things that you used to be able to reach with the 64 by 64 subarray. And then if you're in the 64 subarray, you can now go 2.5 magnitudes brighter than that. So all the way up to magnitude of 3 in K that you can image now with NIRCam. And then here's a summary of the different stripes that are available. There's 4 for the full frame and 3 for the subarray. And then the numbers here are telling you how many rows are in, how many science rows are in the stripe. And then in this table, which is available on JWST, it'll also tell you how many stripes it takes then to cover the frame. So the smallest one, for example, takes 255 of these stripes to cover the entire frame. And then it also tells you how many reference pixels you get for each one, and then the brightness limit improvements for each one of these. So take a look on JWST for details on these. And then a couple words about how you implement this in ETC and APT. It's really quite simple. Everything happens really behind the scenes here, and all you really need to do is select the subarrays. So I've just taken screenshots here of the time series mode and the imaging mode and shown you that in the subarray pull down in APT, you just pick the subarray and that's all you have to do. And then this one below it is just scrolling down so that you can see the 64p ones are also here, along with the normal subarrays, which are here. And then in imaging, it's the exact same thing. You have all the full super stripes, and then the subarray super stripes are down here. And then in ETC, it's exactly the same thing. You just go to the detector setup tab in the ETC and pick your subarray, and that's all you need to do to use this mode. So this is going to be available in, or is available in the Cycle 6 call for proposals, and we'll be working on calibrating it and characterizing it over the next year until Cycle 6 starts. The next mode is the moving target shadow observations. So this is the getting away from multi-stripe for a second. So this applies only to imaging and only to moving target observations. And the problem is that when you're looking at a moving target, you're following your comet or your asteroid or whatever, and all of the stars and the galaxies in the background are streaking across your frame now. And the pipeline interprets these as transients and tries to subtract them. But you end up with pretty messy data like this. It doesn't do a very good job subtracting them because they're not actually cosmic rays or anything like that. And in many cases, you have your very faint, interesting target down here with all of this contamination from the background objects in the way. And so the solution is to do shadow observations where you go to the well, here, I'll show you here. You go to the same location that you were at when you observed your moving target. You wait for the moving target to get out of the frame, and then you do the exact same track. And then you have an image of the background stars and galaxies that's exactly the same with and without your moving target, and all you have to do is subtract them. And this is now supported for, you can do it with dithers, you can do it with multiple filters, you can do it with mosaics, but you can't split the visit. If you split the visit, you'll have to do separate observations. But the result is shown here for just an example. The comet is super faint here, so you can really barely see it at all. But you can see how well most of these stars and galaxies are subtracted out. There's a few sort of positive negative pairs here that you can see, and that is from this sort of 1 pixel pointing error that you get in this mode. So the stars and galaxies aren't quite perfectly aligned in the pipeline, but of course you could take the data offline and try to do a better alignment and subtract them a little bit more cleanly. And also note that this is first implemented for NIRCam, but MIRI and NIRSpec are also working on shadow observations, and those are all those commissioning observations are underway and still being worked on. So in the end, when you put it all together with multiple dithers and mosaics, you'll get something like this, where your little comet is going here and is nice and clean. All of the stars around it have all been subtracted out, and now you can do your analysis. All right, so to do this, or to implement this in APT, the only thing you need to do after you set up your moving target observation is to go into the special requirements and add a moving target shadow observation with the interval that you need in order for your target to move out of the track. And once you do that, it automatically generates a position angle constraint, and it automatically generates a target for your shadow observations up here. And so all you need to do is create this special requirement, and that's it. All right, so the last one that I was going to talk about is the shortwave GRISM time series, and this is bringing us back to multi-stripe again. But let me just explain what we're using here. So in our GRISM time series mode in the past, we only had the long wavelength channel available because we only had GRISMs in the long wavelength channel. And in the short wavelength channel, you still got data, but you could only do imaging. And that was because we just didn't have GRISMs in the short wavelength channel. But in commissioning, we had something called the dispersed Hartmann sensor, the DHS, and that was designed to support mirror phasing and alignment during commissioning. And what it is these little sub-apertures. So this is an image of the mirror here, and all of these brighter rectangles are these sub-apertures, which are basically GRISMs. And so we basically have 10 GRISMs sampling small parts of the mirror. And each one of these sub-apertures creates a spectrum across the short wavelength detectors. And at this rotation that we're using for science, this is where they all land. So sub-aperture 5 is here, and 4, 3, 2, 1, and 6 actually fall off of the detectors. So those are not actually used for science. And you end up with 8 spectra across the detectors for your source. And so this is one source with 8 copies of the same spectrum. And so one of the advantages of this mode is that because these apertures are so small, you can actually observe very bright objects in this mode. And the first validation observations for this were taken just about a month ago or so. So we're still working on it, but I'm going to show you some sneak peeks in a minute. But first, a few more descriptions. This is the where the spectra will be on the short wavelength channel, and then the long wavelength, you still get that simultaneous in this mode, which is just going to produce one spectrum in the long wavelength channel. And so altogether, you have a spectrum from 0.6 microns to 5 microns. The resolution in the short wavelength channel is about R300, and in the long wavelength channel, about 1600 at 4 microns. And then to read these spectra, we use the multi-stripe mode, which you've already heard a whole bunch about. And so we actually produce stripes, detector stripes around each one of these. And you can choose how large those stripes are and how many of them you want to read. And that will determine your brightness limits. And so we have 4 options here. The first number, 41, is the number of rows in the substripe. The S1 refers to how many substripes are in each one of these 4 detectors. And the 2 refers to how many total spectra you get. And that all put together affects the frame time, so that the smallest one is about 0.2 seconds. And then there's some details here about which stripes are included and the total stripe time. And I'll just note this table is on JDocs. So altogether, this is just showing you examples of all of the different filter combinations that you can use in the long wavelength and short wavelength channels. So we can do all of the wide filters and the extra wide filters in both channels. And this is showing kind of a stack from the two different field points, the F322W2 and the F444 field points, which just move, the star back and forth depending on which filters you're using. And then the stack here is showing, I have outlined in yellow, the long wavelength spectra. You get 4 copies of that because we've had to read it 4 times for the short wavelength channel. And then in the short wavelength channel, you get all 4 detectors here. And where the spectrum is depends on which filter that you use. So in this case, for F200W, the spectrum is over here on A1 and A2. But then you can see that depending on which filter you use, you might end up cutting off your spectrum. For example, this one here, F115. And in that case, you might want to use the other field point, F444W, where now you get the whole spectrum spread across the two, all 4 of the short wavelength detectors. So depending on which filter you're using, you have to be careful about exactly where you're placing the target and which filters you're using. So here is a sort of a sneak peek on what the data look like. This is an observation from program 9215 of a calibration star, and it is in F150W2, so you can see the spectrum stretching across all 4 detectors. And then down here, I'm showing just the 1D extracted spectra from detector A2, so this one up here. And when the star is at the 322W2 position, you get a lot of contamination from the second order here, so you have to be careful about that. But when you go to the other position, 444, you don't have that contamination. It's nice and clean. And the data look really fantastic. You see lots of really nice lines and features here, and really low noise in this observation. And then we had another program 9243. This one looked at WASP 18b, and this is just basically straight out of the pipeline. It's a white light transit curve from just substripe 7, so just one of the substripes on NIRC A3, and it's showing already 1% precision just from this one substripe. So when you combine them all, you're going to improve this significantly. All right. So this plot up here is showing what the new bright limits are for the short wavelength GRISM time series. Depending on which substripe combination that you use, it changes a little bit, but it ranges from a K-band magnitude of 1 to -2. So this, we can really go very, very bright in this mode. And then of course, this is the sort of into reads what you get. But for your own targets, you need to go into ETC and calculate it yourself. And to do that, there's actually 2 things you need to do. One, you need to pick the subarray, just like in the other modes. Pick which substripes that you're using. And then you also need to specify the PSF type. So tell it, are you using 2 spectra, 4 spectra, 8 spectra, etc. And that will give you the saturation limits and your signal to noise limits for the ETC. And then in the APT, all you have to do is pick the subarray, and of course the filter too. But it's just one of these 4 subarrays, and everything else happens behind the scenes. So that is it for NIRCam. Just as a summary, we have this superstripe capability that allows you to image these larger, very bright targets. So it opens up a whole slew of new opportunities. There's things like Jupiter. There's also, the Orion or globular clusters or the centers of nearby galaxies that all previously needed to be observed in subarrays. The full frame bright limits have improved by almost 6 magnitudes, and the 64p bright limits have improved by about 2.5 magnitudes. And the moving target shadow observations are now operational, and we encourage people to use these. And then now shortwave GRISM time series is also operational. And I just want to say, both of these, moving targets and shortwave, were both enabled in the previous call for proposals, but the data have only recently been taken. So that's why we wanted to show it off today. And then I also have a link up here pointing to some ETC and APT updates that might be helpful from a previous JWebbinar. And then down here, just a couple of links to some calibration papers that came out this year for NIRCam. And that's it.